what's going on here. Okay, so for question 2, I had to restart, but we're going to come in fresh, alright? We're dealing with this signal here, right? Part A of question 6.93-9. Find the exponential Fourier series for this signal here. And to do so, we must use the formula. X of t is equal to the summation of n equal to negative n as goes to infinity. So we have d of n and we have the exponential on the right. So we must use this to find the periodic Fourier series, because this is a periodic function with a period of 8, by just looking at it from -4 to 4. We get the same point or repeated signal, and it starts all over again. That's how we know it's a period of 8. So we must then now break up this signal like we did with the trigonometric version, but you don't really have to do that since we have e, we're using the exponential, and an exponential represents both cosine and sine. So, like we did before, we have a sub 0, which is the function, I think it's a dc part, the function, just basically the area of said function, which should be 0, right? Because if you grab the area under and over, like so, we'll get 0 of that part. And it's the same on the right, so you could just multiply that area by 2. But what do we see about this function? It is an even function. This is an even function. So it only has a real portion, right? There's only cosine. And if it's odd, then it has an imaginary portion only, and that would be sine. So this is me finding a sub 0, and I get 0 obviously because the area for an even function, and for this one specifically, it's going to be, since it goes under and over the x the same amount, we'll get 0. So to set this up, right, and we also know that, let's see, that from it's 1/2 t plus 1 is our mx plus b. That is this line here. And if we integrate from -4 to 0, 1 over 8, that's the period. X of t is going to be 1/2 t plus 1. And what is going to be our exponential? Since we know it's an even function, it's going to be cosine. Cosine of what? Well, inside the exponential is going to be n omega naught t. Even function. Okay? dt. Okay. So we have that. Whew. Now, let us solve it. So we can distribute the cosine. So we'll have 1/2 t. Let me zoom in a little. Cosine of n omega naught t plus cosine n omega naught t. And we could do that same trick where we multiply the final answer by 2, because the area on the left of the signal must be the same on the right because it's an even function. And we'll pretend the 1/8 is out here. And we know that omega naught's going to be 2 pi over the period 8, which is pi over 4. So let's keep going. We'll integrate the one on the left with integration by parts. We'll let we'll do t is let u equal t, and dv equal cosine of n omega naught t. Du is equal to dt, and v, if we integrate that, well, let's see. We'll get 1 over n omega naught. How do we get cosine? A positive sign. Sine n omega naught t. Okay. Okay. Let's keep going forward with this. We're going to do uv on the left, t over n omega naught, sine of n omega naught t. Okay. What is that, 1/2 there? Let's bring that down or else we'll get it wrong. Then we'll have minus the integral from -4 to 0 of the 1 over, we'll put that constant outside. That doesn't look good. Do this. Okay, now let's integrate that. To get a positive sign, we would need the derivative of cosine is negative sign, so we'd need a negative cosine to get a positive sign. So it's going to be 1 over n squared omega naught squared on the outside. And the negative will cancel with the negative from the cosine. Okay. And we'll evaluate these from -4 to 0. We'll rewrite it as follows. Okay. So let's evaluate this. So on the left side for the first one, we'll know 0 will make everything go away. So let's focus on -4. So when we subtract the lower portion, it'll make a negative. And that -4 will cancel out with that. So we'll get a positive 2 over n omega naught plus that 0 inside the cosine will make the whole thing turn to 1, so we'll be left with 1 over n squared omega naught squared. And then we'll have a -4 inside there, so we'll make it minus 1 over n squared omega naught squared cosine of -4 n omega naught. Okay. Now let's evaluate this right side here. We ignored that one and left it for last, so we know that this, the integration for cosine, is going to be, if we want a positive cosine, we need a sine. It's going to be 1 over n omega naught sine of n omega naught t from -4 to 0. 0 for sine is 0, so we'll focus on the -4. Okay. Forgot to evaluate this. There shouldn't be a t in there. Should be a -4 and omega naught. Caught that one. That's going to be a sine. Negative 4n omega naught. Okay. Now, what can we do from here? We know that this can simplify to 2 over 1. Okay. And we see some common things here. Okay. Common sign. We can add those together. So we'll get, what, 3? If they have a common denominator, we'll get 3 over n omega naught sine of negative 4 n omega naught. Okay. Okay. So now we have, let's see. So, we are, okay. We'll bring everything down first. Okay. Let's see what we have here. Alright. Now this could be simplified further. Some sort of way. Let's factor out a n squared omega naught squared. Let's do that. Let us do that. We'll do, or you could just really leave it if you wanted to. So this would be equal to our d sub n. And, and, if we plug that back into our equation, right? X of t is equal to the summation of d sub n e to the j n omega naught t. Right? We'll pretend we're putting that in there. And that should be your answer for this equation. And when we're solving for all of this here, we're solving for d sub n, the coefficient connected to this exponential. So yeah, that should be this answer done. Alright, so for this one, for part 7.1-5, this is the third question, I believe. We must find the Fourier transform for the signals x of t in these figures, a and b. Okay. So how do we do that? Well, we know that since these functions go from 0 to infinity, whatever that may be, 0 to t, and not from 0 to negative infinity, it does not include that, we can use the basic Fourier transform for said function. So this integral goes from 0 to t. I hope you didn't hear that. E to the negative t is the function, and the Fourier transform is e to the negative j n, no, n is for periodic, omega t, right? I believe so. Okay, so let's integrate said function. So we know that exponentials that are multiplied together can be added together. So we know that can be replaced with, we'll factor out that negative. I don't know what just happened there. T, and we'll factor out the t as well. We'll factor out a negative t. All right, we can factor out a negative out of both. Okay, and the t. So we're left with such. And let's integrate this first. Let's insert a blank there. Let's integrate this. We know that e to the whatever, right, will be 1 over negative a plus jw e to the negative t a plus jw dt. You should know how to integrate e's by at some point, right? Should be good at that. 0 to t. Then you plug in your t at t. So you'll have 1 over negative a plus jw e to the negative t, doesn't change, minus, make it a plus, because this negative here will cancel out with the minus. E to the 0 is just 1, so we'll get 1 over a plus jw. And that's our Fourier transform. To represent the Fourier transform, we'll say x of omega, right? Frequency. They're in the frequency domain. Now let's do the same thing for the other function, e to the at, which it's going to be just as easy as this one. We're going to integrate it like so, from 0 to t where it exists, and the function is e to the positive at times e to the negative j omega t times dt. This, to note, just like in Laplace, e to the negative st, is our conversion, taking our function x of t to the frequency domain. When we use the same function, e to the negative j, whatever the frequency being, for our periodic functions as well as we did up top, right? We take apart our signal. It's kind of what it's doing. Kinda. It's what it's doing. So now let's solve this. So we'll get combine them like we did before, add them. This time we can't factor out that negative. dt, integrate 0 to t, and we'll integrate that. We'll get 1 over a minus jw e to the t a minus jw, and to do that from t to 0, and we'll get the same thing again. It's not good drawing or writing. E to the t, plug in t at t, just get the same thing, and then we'll get minus 1 over a minus jw. You could simplify this. They have the same denominator, but I'm not going to do that. Equal to the x as a function of frequency. Okay, so that's our solution for part 2 of the other drawing. So now we go on to number 4. Okay, so for 6.4, we'll do part A first. Find the exponential Fourier series for the signal x of t. You can do this without evaluating any integrals. Okay, so we don't have to evaluate the integrals. So cosine of 5t and sine of 3t, we can't exactly evaluate that just as is. We kind of want one single function to define everything. So we're going to use a trigonometric identity. We're going to do cosine of a times sine of b is equal to 1/2 sine of a plus b minus sine of a minus b. I don't know how I remembered that. Thought I'd have to go look back. Okay. So we know that 5t, this is a, this is b, will simplify down to sine of, good lord, 8t minus sine of 2t. Okay. And now we have two different functions that we can evaluate and look at. 8t divided by 2 and minus sine of 2t divided by 2. They're separated by that minus. Alright, so where do we go from here? Well, what the hell? Oh, I didn't mean to say that, my bad. Pretend I didn't say that. We need to convert this into its exponential form since we're doing the exponential series. Fourier series for this. So, if we factor out this 1/2, we can convert it directly. E to the what? What am I doing? E to the theta, where theta is at. Okay, e to the j a t over 2j. Come on now. And as I was saying, you can transform the signs into this Euler's form, right? Sine, this is the general form for transforming sine. So, from here, we'll factor out the 2j, right? Pull 2j out. I'll get 1 over, insert a blank here, 4j, e to the j a t minus e to the negative j 8t minus e to the j 2t plus e to the negative j 2t. Alright, so how do we convert from what we have here to the Fourier series? Well, it's a good thing to note that functions like the ramp, the square waves, the whatevers, all those waves, they have, they need to be filtered out, right? That's why we use the e to the negative j omega t to filter out, right, the signal that we're looking for the Fourier series. I don't know exactly what the importance of it is, but that is the filter. We don't need to filter sine, right? Sine is orthogonal and cosine. You don't need to filter it. It doesn't require a filter. So this is a good enough form for the Fourier series. So if we go and look at the harmonics are what I would call, we have e to the j n omega t. N, which refers to the harmonic portion of the summation. Let's say our 8 is our n, right? And then we have c of negative 8. These are just the coefficients. This coefficient connected to it. And we have, that'll be negative 1 over 4j. And we'll have c of 2 and then c of negative 2. Negative, positive, right? You see how this is kind of oscillating? Just like a sine wave. And that's a good thing to note, for sure. So now we must plot a phase spectra. And what that really is a plot of, on our x-axis we have n, and on this we have our phase angle of c of n. And we know if c only being imaginary in this case, we'll focus on sine. Where is sine positive, right? If we only have a positive sign, we are at pi over 2, negative pi over 2, negative pi over 2, and pi over 2, and so on. And we know that at 2, negative 2, and then at 8, negative 8, and we'll have from pi over 2 to negative pi over 2, something like that. So we have, this is a discrete kind of graph, by the way. Negative pi over 2. So we're going down for C2. And for negative 2, we're going up. And for negative 8, we're going down. Right? Really? Yeah. And for this one, we're going up. And you can kind of see the sine wave. I don't know if it correlates to that, actually, at all. But you kind of see it oscillate like a sine wave. Kind of would. Possibly. Just forget what I said. Okay, and that's part B for this question. And then we have part C, which is the signal x of t is applied to the input in LTIC system with a frequent response as shown in figure. Whatever, find the output y of t. Well, those harmonics we just found, 8, negative 8, and 2, and negative 2, all fall outside of this filter, right? Whatever this is, this system, and is only on u of t, which states when it is on and off here. So if we pass this signal through, it won't exist at all. Its frequency lies outside the range. So y of t, right? Y of t is equal to 0 because w is not in the filter. Okay, Patrick. Alright, now we have question 5, which states we have a transfer function and we have an input function, and we need to compute the output y of t. Okay. Alright, so now we're going to do question 5, which states consider an LTI system with the transfer function, and we need to compute for the first problem the input x of t. The most important part is doing this, computing the input with the transfer function. But we want the output. So if we have an LTI system and transfer function and an input, now it's important to notice these bounds, right? Your first instinct would be, oh, let me Laplace x of t and then multiply them together. You can't do that because Laplace only exists from 0 to infinity, right? That's only where Laplace can exist, because if you have, when you integrate Laplace, like when you transform them with e to the negative st, if you have a negative infinity up here, that negative will cancel with the negative infinity, make it positive infinity, and it's not decaying any longer. And we need the exponential that we're transforming it to decay to break apart the function. So enough yap yap. So we have said transfer function and input. What we need to do is use this formula, right? When we have a transfer function and input, if you want to find y of t, the output, we need to do h of... I wonder how it sounds. Does it sound bad? Does it sound good? I don't know. Hello? What about this? How does this compare to that? I don't really... Alright. So,
since we are computing the input into this transfer function up top, so how do we do this? The basic form is y of t, right, is equal to h of s times x of t, right? So what do we need to do? So it's a good thing we'll start with off looking at x of t, 2t. What is that saying? Well, it has an angular frequency of 2, right? And when you multiply the input into this transfer function, that angular frequency is not changing. But the amplitude and the phase angle, or phase shift, the phase shift will be changing, right? So in your final answer, we need to evaluate what the amplitude of the transfer function's frequency is to see how it affects, we need to grab its magnitude to see how it affects our amplitude, how it affects this 3, and we need to find the phase angle at that frequency, right? It's all about at the frequency of the input, right? We're evaluating the transfer function at the frequency to see how it affects the amplitude and the phase shift. But the frequency is not changing. As you see here, it is still 2t in our final answer. So, without all the yap, we need to evaluate magnitude, angle frequency, phase angle, angle of the transfer function at 2j. And 2j, the 2 is from the angular frequency of cosine. So you see that has 2t, so it's going to be 2j. Plugged in at s. We say s is equal to 2j, right? And if you want a general formula, we'll say s is equal to jw, where w is the angular frequency of whatever is inside the input. All right, so how do we find the magnitude, right? How do we do that? So we're going to plug in, into the transfer function 2j wherever there's an s. So we have 2j plus 1, 2j squared, plus 2j plus 2. Let's simplify the bottom. It can be done. So we'll have 4, 2 squared is 4, j squared is negative 1, plus 4j plus 2. So we're left with 2j plus 1 divided by 4j minus 2. Okay. And how do we grab the magnitude of this? Well, it's normally how you would calculate magnitude. We know that a squared plus b squared, right? The square root of that, this is magnitude, right? So what is a and what is b? Well, that'll be a real and imaginary part. So for example, you'll do 2 squared plus 1 squared, square root that, and you'll get what? Root 5 on the bottom. We'll do the bottom real quick. It'll be 16 plus 4, which is 20. Okay, and we can simplify 20. We know that 20 breaks up into 4 and 5, 2 and 2. Group the 2, and we know we have root 5 over 2 root 5. And if you don't know how to do that, simplification of a square root, that's not good. You should be something you know by now. And we know that it has root 5 on the top and bottom cancel out, and we're left with 1/2. So we got our magnitude of h of 2j as 1/2. Beautiful. All right. And now comes the harder part, the angle. All right. So how do we compute what we have for the phase angle of h2j? So to find the angle, so we know that to evaluate h at 2j, it's going to be 2j plus 1, 4j minus 2. This is equal to h at 2j. Right? So what is the phase angle of h at 2j? So that's going to be the angle of the top of this minus the bottom phase angle down below. Right? So when you have it in phasor form, this division symbolizes subtraction for phasors. And we're more concerned about the angle, not the magnitude of said thing, because we already figured that out, what the magnitude's going to be. So, interesting. Made a few realizations myself. We'll just keep going. I don't want to explain it another way. But this should be good enough. So we're going to find out what the angle is up top. You could have just made this all phasor and just did it straight up. Ignore what I'm saying. What is my battery on? Uh-oh. Let me adjust this really quick. 1 sec. Alright, so to find the angle of any phasor, you should know this if you've taken 202. You must take the imaginary part, inverse tangent of that, 2 over 1. That'll give you your angle. And then do the same on the bottom, tangent, inverse of 4 over negative 2. Right? And you should get the following. Let me computer real quick. All right, these are the numbers you'll get. However, there are sometimes, the inverse tangent can only give us angles it's limited to, let me think, certain quadrants, right? From time to time, depending on where it is. So it's good to notice and check your work when you look at these. Like, J is the imaginary part, and J associates it with sine, and sine associates itself with the y-axis. Yes. And the real part is cosine associated with the x-axis. So these are both positive, so this should be in the first quadrant, and we notice that 63 degrees is in the first quadrant, so it's fine. But with the second one down below, we see that y is positive, but x is negative, right? Where's y positive, but x is negative? That is the second quadrant, right? It is located here. Well, negative 63 degrees is somewhere from the starting point here, will be around here, right? That's not in the right spot. So we need to rotate this by adding 180 degrees to its rightful spot. And that's going to put it at, I didn't calculate that, plus 180. 116.56. Okay, so let's subtract those two angles. 63.43 degrees minus 116.56. And we get negative 53.13 degrees. All right, now let's put our final answer all together. We know that the cosine of 2t, the frequency doesn't change, but we'll have a phase shift of 53.13 degrees. And our amplitude was 3, but it gets multiplied by 1/2, which makes it 3 over 2. And this is equal to y of t. Voila. That is our answer. Lovely. That will finish all the questions on this homework. I think next I'm going to do questions for the, questions for the midterm exam. A bunch of those. All right.